Hello everyone, welcome back to the Data Science Exam Preparation Series. So in this video we are going to start question number 4 and trust me, this question is very interesting. Part A is about important feature engineering techniques and part B is about sampling from distribution including inverse transformation sampling and Monte-Carlo sampling. So let's begin. First, what is feature engineering? Feature engineering simply means transforming raw data into a better input features so that a machine learning model can learn patterns more effectively. So here are four important techniques. First one is normalization, second one is binning or discretization, third one is one hot encoding, and last one is label encoding. First is normalization skill. Used on continuous data, bring values into one common scale, for example converting age 0 to 100 into 0 to 100. Useful for neural networks, logistic regression, KNN and SVM. So normalization basically continuous numerical variable usually have different ranges. So normalization scales the value into a fixed interval. So for example, we see the example like age value into 0 to 1 scale improves gradient based model such as neural network and logistic regression. So after discussing normalization, we are moving ahead with the one hot encoding. One hot encoding is used for categorical data like creates dummy columns, example color, red, blue, green. These are three binary columns, useful for logistic regression, SVM and neural networks. So many machine learning algorithms cannot directly work with categorical columns. So one hot encoding creates a separate binary columns which are having 0 or 1 values for each category. This is the concept of one hot encoding. After that, moving ahead with the next process, binning or discretization. Discretization, binning converts a continuous variable into a discrete categories. Like it is apply on the continuous data only. So convert continuous value into ranges, for example, age into teen, adult or senior. These are all the categories. So it is useful when data is noisy, capturing non-linear patterns. Binning example is age 1 to 100 can be converted into age groups. So here we have written three age groups like child, adult and senior. This helps reduce the effect of noise and captures non-linear relationship in the data. It is useful in decision trees, credit risk prediction and medical analysis. Last one is label encoding. Label encoding assigns number to categories. Example male 0 and female 1. So like assigning an integer value to each category is the concept for label encoding. So it is mainly used when categories have an inherent order, which is education level, primary, secondary, and graduate. It reduces dimensionality compared to one hot encoding, but may introduce artificial ordering if used incorrectly with the nominal data. So for these whole answers, we had the summary like normalization for continuous value, encoding for categories, binding for ranges, and label encoding for ordered categories. So together, these techniques improve machine learning quality of ML models. So, moving ahead with the next question. Here, the next question is, what is a sampling from a distribution? Describe inverse transformation sampling or Monte Carlo sampling with an example. So, basically, we are going to discuss this question. Before discussion, tell me what is sampling from a distribution. So, it is the concept sampling means generating random values that follow a given probability distribution such as uniform, normal and exponential. For example, if I sample from normal distribution, most values will be near the mean and few values are far away, exactly like a bell curve. So sampling from distribution is a great example like bell curve. Okay. So moving ahead with the inverse transform sampling. Inverse transform sampling is a method for generating random values from probability distribution using a uniform random variable between 0 and 1. To generate U from uniform 0 to 1, compute inverse, then output that value as sample. Example here is exponential distribution. To apply the inverse CDF, we have this formula written on the screen, x equal to f inverse of U. So this is inverse transform. Now next is Monte-Carlo sampling. Monte-Carlo sampling refers to generating large number of random samples and estimating probabilities, expectations or integrals using these samples. So idea here is instead of solving a mathematical problem analytically, we simulate random number and compute the answer numerically. So here the example written, and also we have this example written for inverse